Hey everyone, today I want to talk about a very useful tool for students or researchers wanting to learn about the Euler Lagrange dynamics formulation. So it would be very useful for people working in controls theory, which would help them model their system and do simulations. Um, this is the website provided by MATLAB, and all you have to do is just download this package. I tried this system with a 2 degrees of freedom robotic manipulator, as well as a 4 degrees of freedom robotics manipulator. And so if we go I guess we can start by looking at the function itself, which computes the Euler-Lagrange dynamics. Basically, they do include some examples of basic systems like this projectile motion, the regular pendulum, double pendulum, and even RLC circuits. Basically, this just computes the Euler-Lagrange equation to find the dynamics of your system. So it just does a lot of differentiation, and it just computes it and returns you the equation that the equations of motion you are looking for. So this example is one I did myself. It's on a 4 degrees of freedom robotic manipulator, as I said earlier. And so you just start by defining your system variables as symbolic variables. So that would be like parameters like your masses or lengths or even gravities. And what you do from there is you first want to derive the equations for the kinetic energy of your systems. This is what we do here. And then after that, you also want the equation for your potential energy. And here you take the difference to define the Lagrange equation. And these parameters here, these are going to be your state variables. These are your internal inputs and external inputs. So if you have motors acting on your joint torques, that would be external inputs. And I believe these are the Rayleigh friction term. And then these are going to be your parameters, the masses and the lengths, which we defined previously up here. And all you do after is just call the Euler-Lagrange equation. And depending on how big your system is, it might take from a few minutes to compute to several days to compute, depending on the complexity of your system. And then this last line here, which is commented out, it basically just simplifies this output even further. This function here, when it returns the results, it may not provide the most simplified function, the most simplified results. So you might want to try to do this if you are looking to get simpler results. So just for this test, we're going to comment it out and run this simulation or this computation. So now it's running, and You'll know it's done running when this turns back to the green play button. But as you see, it's only a 4 degrees of freedom manipulator, and it does take a bit of time to compute. So let's just wait a little bit here. And here you go. So to find the results or the dynamics equations, so you just go in your workspace and look for this variable VF, and so here you go. So it's gonna, so for a 4 degrees of freedom system, it's gonna return 8 equations. The first equation is always the derivative, and then on the second ones you get your nonlinear system equations for that particular joint. So you can copy these, and this is what I did. I just copied them in a Word file, a Word document, and I just copied the second, fourth, sixth, and eighth equation because if you go back, the first, third, fifth, and seventh one are all just the derivatives of that particular joint angle. So we don't really need those, and so because this is a nonlinear system, usually in a linear system you would get the state space model in the form of x dot equals ax plus bu, but because this is a nonlinear system, you can formulate it as x dot equals f of x plus g of x u, right? And so this could be very useful to do if you are looking to apply nonlinear control techniques. So all I do here is just separate these equations based on terms which contain a control input u and terms which do not contain those. And just to add, this d of x, g of x is just an element by element multiplication. And here you go. So now we have all these terms. As I said here, f of x, u, and d of x are column vectors, and this g of x here is a n by n matrix, square matrix. So this n is actually the size of your system, or the amount of degrees of freedom your system has. So now that we defined our f of x, d of x, and g of x matrices, all that is left to do is export them back to MATLAB. Let's close this and come back here, and here you go. We just copied those terms that we have here. So you see here we have d1, d21, d31, d41, and so on. We just copied every other equation, and here we define them as matrices. So all of what this means is that this is going to be our model, which is going to enable us to compute simulations for that 4 degrees of freedom manipulator. Then what we did was we designed 2 controllers. One of them is a feedback linearization controller, which basically just suppresses the dynamics of the system, and has a control law with a PD controller just here. And let's just run the simulation here. And here you go, you see the robotic arm converge to the desired location, which was specified as the desired location was specified here. We can try something else as well. Let's try maybe 30 and minus 65 minus 20. I've never tried this, so let's see what we get. We can even try minus 175 degrees. So let's see. Here you go. So actually here, because we bounded our graph here, we actually are not even able to see. Oh, here we go. But yeah, you do get the idea. You can see we set minus 175, and because we started on this line here on the 0 axis, on the 0 y-axis, we did a minus 175 rotation, and that's basically it. And yeah, the system does converge to the desired location. Additionally, we also tried a sliding mode nonlinear controller, which we can try here. Sliding mode tends to be a little bit more robust in real-world application, but you do see here we do get the same exact result in simulation. And here you go. Thanks for watching.